Have you ever wondered why long aluminum structures have tiny gaps between them? Or why metal roofs pop and creak on a hot afternoon? It's because of a single powerful number, a secret code that tells engineers exactly how much a material will grow when it gets hot. Let's look at a real example. Imagine scientists tell you that the linear expansivity of aluminum is 0.000023 per Kelvin. That sounds abstract, doesn't it? And why is the unit per Kelvin if we are talking about a change in length? Is length not supposed to be measured in meters or probably centimeter? So let's break it down to its most ordinary meaning. Remember our two rules from the last lesson. We always start with a standard 1 meter bar and we heat it by exactly 1 degree Kelvin. So this number simply means if you have a piece of aluminum that is exactly 1 meter long and you raise its temperature by exactly 1 Kelvin, the bar will expand by a tiny fraction, exactly 0.000023 meters. It is telling us just the expansion fraction expressed in decimal for every single degree of temperature change. Now, what if our piece of aluminum isn't just 1 meter long? What if we have a massive industrial pipe that is 35 meters long? How do we find its change in length? We use simple proportion. Think about it. If 1 single meter of this aluminum expands by 0.000023 meters, then a pipe that is 35 times longer must expand 35 times more. It's just like buying fruit. If 1 apple costs 12 cents, 35 apples will cost 35 times 12 cents. So, to find the expansion for a 35-meter bar, when heated by just 1 degree, we simply take our expansion number and multiply it by 35. Mathematically, that is initial length multiplied by linear expansivity. And that gives us the change in length as 35 times 0.000023 meter, which produces the change in length as 0.000805 meters. But wait, what if the hot sun beats down and heats our 35-meter aluminum pipe not by 1 degree, but by 40 degrees? We just add one more simple step to our proportion. If the metal expands a certain amount for 1 single degree of heat, then heating it by 40 degrees means it will expand 40 times more. So we take our previous result and multiply it by 40. That is, we first multiply the initial length by 35 meters, and then we multiply by 40 degrees. Look at what we just did. So to find the total change in length, we multiplied 3 things together. The initial length times the linear expansivity times the change in temperature. Look at what we just did. So to find the total change in length, we multiplied 3 things together. The initial length times the linear expansivity times the change in temperature. And that is the formula we have had on our board all through this lesson. And congratulations! Without memorizing a scary textbook formula, you have just derived the core equation of linear thermal expansion using basic common sense and simple proportions. Total expansion is simply how long it was, times what it's made of, times how hot it got. In our next video, we are going to look at how this beautiful concept layout is organized in arithmetic equations so you can solve any exam problem effortlessly. But before then, we take one more video clip. This time, we explain why the unit of linear expansivity is per Kelvin or per degree Celsius and not meters, as we would have expected a change in length to be. See you there.
Udimking Education Foundation. Building confidence, ending examination malpractice for a better tomorrow.
We are building a better tomorrow.
Join us in shaping futures through integrity and education.